So today we'll start talking about the VSEPR, or again, this should be a review, which is the valence shell electron pair repulsion. The idea here is very straightforward. It's just talking about what exactly is the 3D shape of the molecule of interest. Again, it's part of our classical bonding theory, so it's not necessarily correct, but a very useful model. So in the VSEPR theory, at the bottom line, we have a hypothesis that our electrons repel one another. As a result, the electron pairs surrounding a central atom will stay as far away as possible. So looking at some of the common examples in organic chemistry, so since we're organic chemists, we're only looking at 2, 3, 4 coordination circle. We don't have to go to the transition metal binding circle. Like for example, if we have 2 electron pairs, they will stay as far away from each other as possible, so making a linear geometry. All right, so the electron pairs want to be as far away from each other as possible. So some examples of these linear molecules we will see later on include like carbon dioxide, or we can have acetylene, all right. And when we have like 3 electron pairs, we're looking at a trigonal planar geometry. So the most distance we can get between the 3 electron pairs is 120 degrees. And examples here including like alkene, like ethylene. And for example, if we give you ethylene, and you can predict the bond angle here to be about 120 degrees Celsius. Right. And when we look at 4 electrons, again, they want to be as far away from each other as possible. So we're looking at a little bit more topology, like if you imagine a cube, and the farthest point on the cube to the center of the cube forms this kind of tetrahedral geometry. So when we're drawing the tetrahedral geometry, let's say methane, for example, we put the carbon in the center. We have the 2 hydrogen that are on the plane of my paper. And then you will have like a hydrogen that's wedged out. So when we draw it as a wedge, it means it's pointing towards you. And also another hydrogen that's dashed in to the plane of paper. Like if you have your molecular kit, like you can start to play around with it and get familiar with it. So like in this case, if we define the carbon-carbon bond and the carbon-hydrogen as my plane, so that means I can draw, say on the top, I have a CH3 and my carbon and hydrogen defining a plane, right? So 3 points define a plane. And then you look at this green one, it's pointing towards you. So we want to draw that green one as a wedge. So we do it like this, some green ball, and then the red ball as dash. It's pointing away from you, the red ball. It will become more useful, especially when we start talking about chirality. So if you have your molecular kit, start to take it out and look at it and get used to the wedge and dash drawing of the molecule. Yes. So the question is, do you need a molecular kit? The answer is it's highly recommended. If you have very good 3D imaginary like vision in your mind, then it's okay. But if not, I highly recommend you get at least like a little bit of it. You don't need an entire box. You can say 5 people can share a box, as long as you have something like this, like a few atoms to play around. That's highly recommended. I'll also bring a molecular kit when we talk about chirality to pass around the room, but it's more helpful if you can get hold to it yourself. All right, So back to VSEPR. So basically VSEPR is just an algorithm that gives you a reasonably good estimation on what the 3D geometry of the molecule look like. And there are several general rules you can use to best use VSEPR. So there are two steps to determine the shape of the molecule using VSEPR. First one is you draw the Lewis-Dot diagram to determine the connectivity between the atom. So remember the Lewis-Dot diagram, we went over that together. You'll also get more practice in the discussion worksheet that is giving you a molecular formula. How do you identify the connectivity of the atoms? Right, we have like 6 different steps of Lewis-Dot diagram. You first identify the least electron negative atom, you put it in the center, using the octet rule to solve for the number of bonds. You connect all atoms with single bond, and then put double bonds and formal charges and lone pairs to the Lewis-Dot diagram to make it correct. After we find out the Lewis-Dot diagram, you can calculate the steric numbers. So steric numbers, it sounds sad, but it's actually just the number of atoms plus the number of lone pairs surrounding to the atom of interest. And then you have the VSEPR table to search for that tells you what steric number, how many lone pairs are there, and what are those things representing a molecule. So some example here. Imagine we have steric number equals to 3, lone pair equals to 0. What is a potential molecule? So that's going to be a BH3. Right, so boron making 3 bonds with hydrogen. By the way, this is a violation of the octet rule because your boron doesn't have enough valence electrons, right? And BH3 will have a trigonal planar geometry. Another way we can ask you is tell me what's the molecular geometry of NH3. So we know that NH3, well, nitrogen, hydrogen, 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 and we have a lone pair. So we're looking at steric number equals to 4 and lone pair equals to 1. So my NH3 will have the shape of trigonal pyramidal. All right, so that's what it looks like here. Just knowing how to draw the Lewis-Dot diagram and how to use this table to identify the VSEPR geometry. And let's do like some practice problems together. Right, so first thing, let's look at H2O, which is water. So water only makes, well, oxygen makes 2 bonds, one with each hydrogen, and then water will have 2 lone pairs around it. So in this case, we're looking at steric number equals to 4 and lone pair equals to 2. Right, so going back to the table, steric number equals to 4 and lone pair equals to 2. So we're looking at something called a bent geometry, right? And one thing to note is that when using the VSEPR, we say that the lone pair electrons will occupy more space than the bonded electrons. So that means when we're looking at the bent geometry, normally in the tetrahedral geometry, we're looking at a bond order of 109.5. So here we say in the bent geometry, the HOH bond angle is going to be smaller than 109.5. And it's a bent geometry. All right. So this is just a quick refreshment on your memory in VSEPR. And before we move to quantum bonding theory, we have one more concept I want to, again, emphasize. That is the polar and nonpolar molecules. So in here, when we're talking about polarity, we already went over like the discussion of a polar covalent bond. That is whenever you have like say in this case, right, as well, like a haloalkene, your carbon is less electron negative than chlorine. So we are having a partial negative charge on the electron negative chlorine and a partial positive charge on the carbon adjacent to the chlorine. So that's a polar covalent bond. But when we're looking at the entire molecule, remember the dipole moment may be canceling out with each other. So now taking together the polarity of the covalent bond and the shape of the molecule, we can predict whether or not a molecule is polar or nonpolar. So let's look at two examples together. One example, like CO2, right? So we draw the Lewis dot diagram and we know that CO2 is a linear molecule with lone pairs. So for each of the carbon-oxygen bonds, it is a polar covalent bond because your oxygen is more electron negative than your carbon. So we have two different dipole moments pointing from carbon to oxygen. However, these dipole moments are exactly the same magnitude because both of them are carbon-oxygen double bonds. They are exactly opposite in direction. So they cancel out with each other, making the CO2 a nonpolar molecule. Or we say that CO2 doesn't have a net dipole moment. All right. Alternatively, let's look at water again. We just did a derivation that water is a bent molecule. So this bond angle here is smaller than 109.5 degrees, right? So likewise, oxygen is more electron negative than hydrogen. So we can write dipole moment for both chemical bonds. Now, in this case, my dipole moment will not cancel out with each other. Now, on the x-axis, yes, it will cancel out with each other, but along the y-axis, it does not cancel with each other. So as a result, we say that water will have a net dipole moment pointing to the y direction. Or we say that water is a polar molecule. All right. So that's about it for the classical bonding theory. So remember, classical bonding theory, we start with the hypothesis of treating electrons and nuclei as charged particles. They're not necessarily correct, but classical bonding theories are very useful, and we will continue using that in organic chemistry. And in classical bonding theory, we went over topics including Lewis dot diagram, VSEPR that tells us shape of the molecule, the polar covalent bond, non-polar covalent bond, polarity of the molecule. And that's about it for the classical bonding theory parts. Any questions before we move on to quantum bonding theory? Yes?
Can you explain how you were able to tell with the x and y axis which cancels and which doesn't?
Well, so here's the thing. When we're looking at these dipole moments, we see that both of them are pointing from the hydrogen to the oxygen. All right, so in this case, these two in the x direction, they're pointing towards each other. And since we're both looking at oxygen-hydrogen bonds, in the x direction, they will cancel out with each other. But along the y-axis, they're working along with each other, so they add up. Right, so it's like vector addition. All right, so let's get into quantum bonding theory. So starting from quantum bonding theory, we're actually talking about the more correct picture of chemical bonds. So there are two different kinds of quantum bonding theory. Both of them will use the concept of atomic orbitals. And then we'll build molecular orbitals from these atomic orbitals. So before we dive in to quantum bonding theory, let's again review what we know about atomic orbitals. So in lecture 1, we went over the concept of atomic orbitals being hydrogenic wave functions. Right? So remember in Schrödinger's equation, We have Hamiltonian acting on a wave function that gives you energy of the wave function. So the wave function is like the oracle. It tells you everything you want to know about the electron. But you have to ask the right question. Now, the atomic orbital are these wave functions for one electron systems, or hadronic wave functions. We have some general pictures about the shape of these atomic wave functions. That is, depending on the quantum number combination, the 1s atomic orbital have the spherical shape. The 2p atomic orbital will have this dumbbell shape. And you have 3p atomic orbitals and 1s atomic orbitals. Right. Now, think about it. We know that these atomic orbitals are wave functions, meaning they behave as a wave. What is the iconic property of a wave? So if we look at just simple plane wave, whenever you have two waves, like two sine functions, meet each other, what will happen? So these waves will interfere with each other. All right? So the first quantum bonding theory is called LCAO-MO theory, or linear combination of atomic orbitals to form molecular orbitals. So the basic hypothesis here is that the wave, or my atomic orbitals, they will interfere with each other. And then depending on whether or not my waves are in plane with each other or out of phase with each other, you can have constructive interference or destructive interference. Right, so this is also pretty straightforward to understand. Like if you imagine these sine wave functions, when your peak meet the peak, you end up with bigger waves. But when your peak meet the trough, you end up with diminished wave. All right, so depending on how you add it, you can have a constructive versus destructive interaction between your wave functions. So following that, we look at our molecular orbitals coming from the linear combination of atomic orbitals. What does that look like? So in the LCAO-MO theory, what we're saying is we can use the linear combination of these atomic orbitals to estimate what does a molecular orbital look like. Okay, so let's look at a simple example. That is, on the left-hand side, we have the 1s of, say, a hydrogen. On the right-hand side, also 1s of a hydrogen. So when these orbitals are infinitely, indefinitely away from each other, like super far away from each other, these waves don't talk to each other at all, right? So each nuclei will hold its own electron, and we see two distinct s atomic orbitals. Now bringing these two waves together, remember we have two things that can take place. When these waves meet each other, it can meet with each other in the constructive fashion or a destructive fashion. So what's going to happen? When they meet with each other via a constructive fashion, what does it mean? It means, well, these waves start to interfere with each other, and we end up with electron density in between my atoms. So this is, on the left-hand side, we have my nuclei 1, and on the right-hand side, we have my nuclei 2. So that's my HA and HB. Now, in between my two atoms, we now have electron density between atoms. And thus, for this constructive interference, we call it a bonding molecular orbital. All right, but that's only part of the story. There's also a possibility of my wave function meeting each other in the destructive fashion. So when that happens, what's going to happen? On the left, that's like phase 1. On the right, that's like an opposite phase. And they will cancel out with each other. And the result of that of that destructive interference is that we end up to have a node plan in the middle of your HA and HB. Or remember, when we say a node plan, that's a low electron density region. Or we call this a anti-bonding molecular orbital. And we can create what we call a correlation diagram based on these two kinds of interactions. So if you look at the actual correlation diagram, what we have is we start from some energy. On the left-hand side, we have the atomic orbital of my hydrogen A. On the right-hand side, we have my atomic orbital of my hydrogen B. Right. And these two will have the same energy. They're both 1s orbital of my hydrogen. So when they meet each other, will form a pair of molecular orbitals. One is going down in energy because it's constructive and bonding. And the other is high in energy, so that's destructive and anti-bonding. All right, and what do they look like? Well, so my 1s looks like a little circle. And in the bonding MO, we're bringing them together so they overlap in the constructive fashion. And in the anti-bonding MO, we're bringing them together, but in the destructive fashion. All right, so that's the orbital itself. And then we can pop electrons into these molecular orbitals. In this case, imagine we're looking at neutral H2. So that means each of my hydrogen will have one electron. So when they come together to form the bonding MO, well, my electrons go to the lower energy MOs. All right. And then we have bonding in between my H2. You can calculate bond order based on this correlation diagram. So my bond order will equal to 1/2 times the number of electrons in bonding MO minus number of electrons in anti-bonding MO. So what is the bond order of our H2? So number of electrons in my bonding MO is 2. Number of electrons in my anti-bonding MO is 0. So the bond order is 1. All right. And let's take one more step. Now imagine, instead of H2, we're looking at a molecule, say H2 minus, meaning we have a total anionic charge, so one of my hydrogen will have 2 electrons in it. What is the bond order of my H2 minus using the correlation diagram? Well, we start from 1, 2, 1 electron. We start from total of 3 electrons. Put it in 1, 2, 3. So now we have 1 electron in the anti-bonding MO. So the bond order of my H2 minus will be 1/2 times, 2 minus 1, and that's 0.5. Right, so it's a much smaller bond order. And like a follow-up question I could ask you is predict the bond length between the H2, the 2 hydrogen atom in H2 minus versus neutral H2. Which one has a longer bond length? Well, so the H2 minus has a weaker bond order. It's a weaker bond, so it'll have a longer bond length. Right, so that's about as much as I expect from you in this correlation diagram. Know how to read it, know how to identify whether it's a bonding MO or an anti-bonding MO. So an anti-bonding MO is having a node plane in between the atoms. The bonding MO will have orbitals in between the atoms, and know how to calculate bond order and to predict some simple like bond length. Doesn't need to be numerical, but relatively predict the strength of the chemical bonds. All right. And reality is always more complicated than H2, right? So I just want to show like some of the more like modern LCAO-MO theories. It's when you have something as simple as CH3 plus. Now, the limitation of the LCAO-MO theory is that these molecular orbitals are always delocalized. Even if we're looking at CH3 plus, you're expecting like 3 CH sigma bonds. But in reality, you're getting something like these. So they're all delocalized over the entire molecule. So that's why LCAO-MO itself, despite its usefulness, we're not going to use it very often in this class. But I still want you to know, like that's the theory behind the molecular orbital. All right. And then I have about 20 minutes left. I want to introduce another quantum mechanic bonding theory. So in MO theory, in this part, we're doing linear combination of the atomic orbitals. Or what we're doing is adding the wave functions together. It's like A plus B, right? So it's an addition for constructive or subtraction for destructive interference. Alternatively, we have the valence bond theory. So the valence bond theory is a fundamentally different quantum mechanical bonding theory. So we're not doing addition anymore. In valence bond theory, we're doing the product of singly occupied atomic orbitals. So keep in mind, valence bond theory, we're taking the product of 2 singly occupied atomic orbitals to predict the bond formation. So in this case, if we're doing the product of the 2 singly occupied 1s atomic orbital, we end up getting electrons in between the 2 hydrogen. And these electrons are indistinguishable. We can't tell where these electrons come from. Well, it's a product of a wave function, so they're like all mess up each other. So if we use F2 as an example, now we have localized bonds. What does it mean? So on the fluorine, what's the electron configuration of fluorine? That's my 2s2 and then 2p5. Right, so that's the electron configuration. And we look at the electron diagram of fluorine. We see the 2s is doubly occupied. 2 of the 2p orbitals are doubly occupied, or these are my 3 lone pairs of the fluorine. In here, we have 1 singly occupied 2p atomic orbitals. So the product of these 2p atomic orbitals forms a sigma bond. Or when we're drawing the electron density or using the valence bond theory, we end up showing like the electron density in my F2 is something like this. We have electron density in between the 2 fluorine atoms. All right, so that's the fundamental of valence bond theory. We're taking the product of singly occupied atomic orbitals. So this is why you need to know how to draw the electron configuration very quickly and then start to do these analysis, because you need to identify which atomic orbital is singly occupied that can be used for bonding. But valence bonding theory itself can easily encounter lots of problems when we look at polyatomic molecules, meaning molecules more than 2 atoms, which is very typical in organic chemistry. So the question here is, how can we use valence bond theory for molecules with more than 2 atoms? So using beryllium H2 as an example, it's already pretty straightforward, only 3 atoms. Now, we have 3 problems if we want to use the valence bond theory as it is, which is the product of singly occupied atomic orbitals. So 3 problems really. First problem, now beryllium has the electron configuration of 1s2, 2s2. It doesn't have any unpaired electron that can form a chemical bond. Right, so the valence bond theory itself will predict no bond formation, which we know is not true. Secondly, the 2s atomic orbital and the 1s atomic orbital of hydrogen will have very small overlap. All of them are spherical, so the overlap is like very small, or the bonding activity we're predicting is small. Problem 3, the 2p atomic orbital overlaps with the 1s very well, like the overlap is right in position, but there are no electrons in the 2p atomic orbital of beryllium. So in order to solve these 3 problems, we end up introducing the hybridization theory. So that's Pauling's promotion and hybridization theory. So it's a clever solution to all 3 problems. So we can use the valence bond theory that tells us where are the localized chemical bonds. So we'll start from the theory itself, and then we'll see the application of the theory. All right. So the theory itself is saying, well, it's promotion and hybridization. When we say promotion, we're saying electrons in paired ground state can get promoted to a higher state. What that mean? Now, if we look at the same energy diagram, we have the 2s and then the degenerated 2p atomic orbitals. Right, so that's what we originally said. So for beryllium, we have 2 electrons in the 2s orbital. So this is the original picture. Now we want to promote one of the electrons into the 2p atomic orbitals. This is called promotion. And we'll be able to get our singly occupied atomic orbitals. Right, so we get our singly occupied atomic orbitals. But this process will be associated with a promotion energy. That's a relative energy between your 2s and 2p atomic orbital. Now, how can we minimize that promotion energy? So the idea becomes, well, why don't we hybridize the s orbital and the p orbital? So we're mixing the s and the p orbital to make hybridized orbitals. So when doing that, we end up getting, we end up getting a mixed orbital that we call sp orbital. So we start from 1 2s orbital, 1 2p orbital, and we end up with 2 hybridized orbital. Right? We cannot create or destroy orbital from the void. We start from 2 orbital, we end up with 2 orbital. And then the other 2 p orbital will remain untouched. And that's called hybridization. All right. So what is the result? We end up with 2 hybridized atomic orbitals that are singly occupied, ready to make chemical bond with the hydrogen 1s orbital. And what is the shape of our sp atomic orbitals? Well, we're mixing a s orbital and a p orbital. Remember what's the shape of the s orbital and the p orbital? Here we are. So this spherical one is my s atomic orbital. The dumbbell one is my p atomic orbital. Right, my p orbital can be different shaded, so we end up with 2 sp orbitals. And these hybridized sp atomic orbitals, both singly occupied, now ready to make a chemical bond with the hydrogen. All right, so back to our beryllium hydride example, what are we having? First thing, we write out the hybridized orbital in beryllium. So that's my singly occupied sp and sp. And then the two px, two py. Not changed. And my sp atomic orbitals are singly occupied, ready to make a chemical bond with the hydrogen. And the result here is we have, well, two single bonds. And if we superimpose the beryllium hydrogen 1 chemical bond with the beryllium hydrogen 2 chemical bond, we end up getting our final product. Yes?
So is only the beryllium hybridized?
So in this case, only the beryllium is hybridized because the hydrogen 1s atomic orbital is already singly occupied. You don't have to hybridize it. But very soon we'll see when we have, like, say, a carbon-carbon bond, then you need to hybridize both carbon. So the whole goal of hybridization is we want to have enough singly occupied atomic orbitals to make chemical bonds. All right. So that's the sp hybridization. We will also refer to this sp hybridization by like percentage of s character. So this one will be like 50% s character, because it's mixing one s atomic orbital with one p atomic orbital. So naturally, 50%. We can do the same operation to form sp2 or sp3 hybridized atomic orbitals, depending on the need. Right, so hybridization actually deeply rooted back to the need of hybridization. It's like, if we look at the steric number in here, the beryllium center has 2 steric number. It's forming 2 bonds, so it must be at least sp hybridized. But if we look at the BH3 or the borohydride, then my steric number is 3. So we're looking at a sp2 hybridization. Right, so the hybridized energy diagram would look like sp2, sp2, sp2. And with a 2p left intact. All right, so think about it. Why do we have 3 sp2 hybridized atomic orbitals? Anyone?
3 bonds?
Well, 3 bonds is one reason. The other reason is we have 3 sp2 hybridized atomic orbitals. We're mixing one s atomic orbital with 2 p atomic orbital. So 1 plus 2 equals to 3. Even me can do that calculation. You see, it's a little bit counterintuitive, right? So we have 3 sp2 hybridized atomic orbitals. We have 4 sp3 hybridized atomic orbitals. And the shape of these sp2 hybridized atomic orbitals are trigonal shaped, because we're mixing 2 p atomic orbitals perpendicular to each other with a s orbital. So we end up with 3 sp2 orbitals superimposed to each other. And what is the s character of the sp2 orbital? What's the s character? 1/3, right? So 1/3 of it coming from the s orbital. All right, and then obviously we have our sp3 hybridization. So that's for our carbon center, the one that we see very often. The steric number equals to 4. So we want to mix my s orbital with all the p atomic orbitals to become sp3 orbitals. So for most cases, just counting the steric number will give you a good idea about what's the hybridization of that center atom. And let's look at some examples together and see how do we use hybridization and valence bond theory to describe bonding in carbon-containing molecules. So we'll look at 3 molecules, and we'll revisit alkenes and alkynes when we get to them in later chapters. So looking at this one, let's see. Yes, so looking at ethane, so CH3, CH3, all single bonds. What does it mean? So we look at the steric number on each carbon, and we see that each steric number equals to 4. So all my carbon atoms will have tetrahedral geometry and also sp3 hybridized. So when we're drawing the bonding in the ethane, what does it look like? So effectively, we'll have a carbon, and they're both sp3 hybridized, meaning you have tetrahedral shaped molecule, hybridized sp3 orbitals. So what does that mean? So I have one pointing towards each other. That's one of it. There's actually like a small one, but you don't necessarily need to show that small one. And you have another one going on the top. And that forms a bond with hydrogen. And another one coming out to the plane forms another bond with the hydrogen. Another one going inside the plane. And in this kind of sketches, we say like this sigma bond coming from sp3 hybridized atomic orbitals of the carbon. And what about this one? This one is again a sigma bond and comes from the sp3 of carbon and 1s of the hydrogen. All right, so that's the single bond version. Let's look at the double bond, because it gets a little bit more fun when we have a double bond to play. So when we have, say, ethane, where CH2 double bonded to CH2. Now for both carbon, we can say the steric number equals to 3, or both carbon will have trigonoplanar geometry. They're both sp2 hybridized. So what does sp2 hybridized mean? So if we look at the energy diagram, we say that the carbon will have sp2, 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 and then a p orbital. And this p orbital will be perpendicular to the trigonoplanar sp2 orbitals. And all 4 of them will be singly occupied. So what does that bonding look like? Now, if we look at the plan of my paper to be the plan of my, let's do this. Let's do the carbon. And we have remember we have the trigonoplanar geometry. So let's do the sp2 of my carbon center. Now this one forms a sigma bond. And then these two will form sigma bonds with the hydrogen. Right, so this gives me my sigma bond skeleton. Now the center one will be the sigma bond between my sp2 carbon. This one will be the sigma bond between my sp2 carbon and the 1s of the hydrogen. However, on top of all these sigma bonds, we have another p atomic orbital that's singly occupied, ready to form another bond. So that's where our pi bond comes from. So that's a p orbital. That's another p orbital, right? So these p atomic orbitals will overlap with each other to form a pi bond. So note that the way we draw it, the p orbital itself is like a dumbbell shape. So in this case, all of these overlaps, they reflect a pi bond. All right, so that's what we call a pi electron. And that's why later on when we talk about alkene chemistry, we see these pi electrons are nucleophilic. Because these pi electrons are pretty exposed. It's ready to react with the electrophilic center. And knowing where these pi electrons are important, and that's why we're talking about it right now. So it's a fun question here. Now imagine we have like a burger. All right, so let's say I put my carbon on both ends, and the hydrogens are around. Now, in this burger, which part of the burger best describes the sigma bond between my carbon-carbon atom? Yes? Yep, so the patty best describes the sigma bond between my sp2 overlap, so they're like meeting each other. What about the pi bond? Which part of the burger describes the pi bond? The bread, but remember, it's both the top and the bottom bread. All right, it's both on the top and on the bottom, so it's like surrounding that sigma bond. All right. And I'm running out of time. I'll pick up from here next Monday. Now on Friday, Dr. Rajat will go over nomenclature of organic molecules with you. So we're switching things a little bit. So he will only focusing on nomenclature of organic molecules. I will pick up from where I left over on quantum bonding theory next Monday.